Hello everybody. Today we're going to be talking about Dalton's Law of Partial Pressures by John Dalton. Basically, whenever you have a container filled with different gases, what Dalton says is that each gas exerts their own individual pressure. We call that a partial pressure. And if you put gases together in a container, what Dalton says is that the total pressure is equal to the sum of those individual pressures. Okay? According to what you see here, it says the particles of different gases in a mixture act independently in exerting pressures upon the walls of the container. Remember that each gas, every time it collides against the wall of the container, that's what pressure is. So, in summary, what he's trying to tell us is that if you want to find the total pressure of a gas, all you need to do is basically, if you get the sum of the partial pressures of all the components in a gas mixture, it will be equal to the total pressure of that mixture. If you could see down here, here's a formula that summarizes his law of partial pressures, where PT is the total and PA would be the pressure of gas A, the pressure of gas B, the pressure of gas C, etc., etc., etc. So all you need to do is add up those individual pressures and you get the total. Now, what I'm going to do is the original Dalton's Law, okay, basically states that we saw that the total pressure is equal to, let's say, the sum of partial pressure of gas A, gas B, and gas C. But I'm going to show you a quick derivative. You recall that the ideal gas law is PV is equal to nRT. What I'm going to do is I'm going to solve for pressure. And when I solve for pressure and you isolate the variable, you get this. Okay? nRT over V. Now, I want you to think about this. Let's say that we wanted to use this equation to solve the pressure of gas A. So we would need to know the moles of gas A, right? The R is actually a constant, so that doesn't change. The temperature and the volume. Now watch what I'm going to show you here. If I were to substitute and I were to put that in place of this here, and then I did this also with gas B, okay? So we'll do this. Instead of putting a pressure of gas B, let's put the moles of gas B times R times T over V. And then let's do the same thing with gas C. And we could keep doing this if there's more gases. Let's just say there's 3. And we add this up like this. This will be gas C. Now, I want you to think about this, okay? If we add these pressures, this would be the partial pressure or the total pressure instead of the partial pressure of gas A. If we put these 3 gases in the same container, I want you to think about this. They're going to have the same temperature because they're in the same container. They're going to have the same volume because they're in the same container. And the R is a constant, so they all have the same R. I want you to think mathematically here. If we were factoring, you always factor by taking out things that are in common. If you notice, RTV is in common for all 3 components here. I'm going to factor that out. And when I factor that out, I'm going to take out the R, the T, and the V. And then look what happens. The only thing that's left is Na plus Nb plus Nc, where it's moles of gas A plus moles of gas B plus moles of gas C. If you multiply that by this part here, RTV, you get the total pressure. Now we can also summarize that if we add these 3 numbers, this would be the total moles. Okay? And this little derivation is going to be useful when you have a mixture of gases and they give you extra information like temperature and volume and they tell you they're in the same container. We can use this new derivation to find the total pressure. Okay? So we'll revisit that as we move along and we'll see that derivation. Here is a summary of what I just did. Okay? As you can see here, I used 1, 2, and 3 instead of A, B, and C. But you can see at the bottom here that as long as they're in the same container, they're going to have the same temperature, volume. R is also going to be the same. The only thing different is you have different amounts of gases, let's say. So you have different number of moles. Okay, they could be the same numbers, but they don't have to be. So this is a new little derivation of Dalton's Law, and that will come in handy in a future problem. Now let's go back and let's analyze the original Dalton's Law, which is this one up here. Let's take a look at a simple problem here. According to this, it says a mixture of helium, neon, and argon gas has a total pressure of 558 millimeters of mercury. So they give us the total pressure. And the units are, again, millimeters of mercury. And they tell us that the partial pressure of helium is given at 341. And it's also in millimeters of mercury. And as you continue reading, the partial pressure of neon is also given at 112 millimeters of mercury. They want to know what would be the partial pressure of argon. So this gas basically consists, or this mixture consists of three gases as stated at the beginning of the sentence. It consists of helium, which I forgot to put the HE here. So it's helium plus the partial pressure of neon and the partial pressure of argon. According to Dalton, if you add up these three individual pressures, they give you the total. Now, what they did in this problem is we're missing this one here. We have helium and neon and the total. So here's one thing you could do. If you add these two numbers up, they will add up to 453 millimeters of mercury. If you subtract that from the total, and this is what I'm going to do basically, if you do this minus the partial pressure of the helium minus the partial pressure of the neon, you will get the partial pressure of the argon. I already added the helium and the neon together, so to find the pressure of argon, which is what we're looking for, all you do is you get the total pressure, which is 558 millimeters of mercury, and then you do minus 453 millimeters of mercury, which is the other two combined, and you get our answer, which is 105 millimeters of mercury, and that will be our partial pressure. Okay? Let's take a look at another example. This one is basically similar to the first one. Here we have hydrogen gas mixed with water vapor. And according to this, it tells us that the total pressure is 745 torrs. They do give you the partial pressure of the water vapor. It's 24 torrs. And what they want us to do is to find the partial pressure of hydrogen gas. So again, what we're going to do is the total is equal to the two hydrogen and water vapor combined. If we subtract the total pressure, which is 745, minus the partial pressure of the water vapor in this case, which is 24 torrs. Okay, I'll put the units in at the end. You'll get the partial pressure of hydrogen, of hydrogen over here. And you're going to notice after you subtract, you get 721. They're both in torrs, so your answer comes out in torrs. So that one's pretty straightforward too. Okay? Let's go to the third one here. Third one's a little different. They want to know the partial pressure of oxygen that a diver breathes with a heliox mixture containing 2% of oxygen. Okay, and it is at a depth at 100 meters. As you go deeper into the ocean, the pressure does increase. And they do tell us that the total pressure is 10 atms. So this one is set up a little bit different. What we're asking is, what would be the partial pressure of the oxygen? So we want basically just the oxygen. What we do is, if you remember from math, 2% of a number, in this case of the total, will be equal to partial pressure of oxygen. And if you do this mathematically, 2% is the same thing, we got to get rid of that percent sign, okay, as 0.02. The word of means times. The total pressure is given at 10 atms. So if you multiply 0.02 times 10, you get 0.20 ATMs, and that would be your partial pressure of oxygen. And that sounds about right. That sounds like 2% of 10 ATMs. So that's how you would do this one. Now, here I gave you the total and I was asking you for a partial pressure. Take a look at this next problem. Here, they give you the partial pressure. It's 0.21 ATMs. What you don't have is the total this time. We know that 0.21% is 5% of some number, some total. So here's how I'm going to set it up. We know that 5% of some number is equal to 0.21, which is the percentage or the partial pressure of oxygen. We're trying to find the total. So if you do the math again and you get rid of the percent sign, this will be 0.05. This will be times the word of. Then we're looking for PT or X. And then that's equal to 0.21 ATMs. So when you set this up in a calculation and you solve for PT, you're going to see that 0.21 ATMs divided by 0.05 will give you the total. And when you do the math, you're going to see that the total is 4.2 ATMs. So does 0.21 ATMs sound like 5% of 4.2? It does to me. That's how you can always at the end check your answer to make sure that you're doing everything correctly. Okay? All right. Let's move on to the next problem. All right. So in order to do this next problem, I have to introduce what a mole fraction is. This is another new formula, two new formulas actually. The symbol for mole fraction is X. Okay? So if you want to find the mole fraction of, let's say, a component, let's call it component A. Okay, I did it over here using the number 1. What you do is you get the moles, okay, of component A, which is symbolized with the letter A, or with the letter N, and then you divide that by the total moles, which we can symbolize it as NT. It's kind of like percent composition, but we don't multiply by 100. So if you were asked to find mole fraction, you're going to see that it's the moles of the component that you're looking for over the total moles, and it will be a unitless number. It has no units because the moles will cancel out. Now, having said that, there's another formula that I'm going to introduce you to, which is right over here. Okay, there is a relationship between mole fraction and partial pressure. And that relationship looks like this. Let's say we wanted to find the partial pressure of gas A. What you do, okay, and I'm going to make this formula linear. I'm going to show you this relationship here. If you want to find the partial pressure of a gas, what you do is you multiply the total pressure times the mole fraction of that gas. But I just showed you how to find this. You would have to do this first to find what the mole fraction is. And then if you multiply by the total pressure, you can figure out the partial pressure. I'm going to demonstrate how to find mole fraction and partial pressure in the next example. Now this problem, the way it's designed is everything is going to be in little steps. Okay? So notice this has several parts to it. So let's begin by analyzing the question. They're telling us we have 480 grams of oxygen. So remember that oxygen is diatomic. I'll do this first part right over here. So we got 480, and I'm doing part A here. And if you recall, since oxygen is O2, if you divide by 32 grams per mole, you will get that you have 15 moles of oxygen. Okay? So this is the answer to part A. That's how many moles of oxygen you have in the tank. Now, it also says that we have 80 grams of helium. So we had 480 grams of oxygen. Now we have 80 grams of helium. So let's do the same thing. This was part A. Let's do part B right over here. So we get the 80 grams. We're going to go ahead and divide that by 4.0 grams per mole off the periodic table. And when you do the math and divide by the molar mass, you're going to get 20 moles, and that's our moles of helium. So we've answered the first two questions, A and B. Now we can also do C right over here. It says what would be the total moles. Well, the total moles is simply 15 plus 20. Okay, so you're going to add that up, and you're going to get 35 moles as your total. Now this would be the answer to part C. Okay, now here's where I'm going to demonstrate what we just learned. Okay, let's flip the page here for a minute. Let's write down the data that we just got. So we know that we got for oxygen 15 moles. Okay, and we know that we got for helium, we got 20 moles. We also know that the total moles is 35. So the next two parts of the question, if we go back here and look, let's find the mole fraction of oxygen followed by helium. So we're going to do two more problems here. Okay, so here's what we're going to do. To find the mole fraction of oxygen, what you do is you get the moles of oxygen, which is 15 moles, and then you're going to divide that by the total moles, which we said was 35. And if you recall, moles will cancel. This is a unitless number. We're going to show three significant digits, and we get 0.429. That's the mole fraction of oxygen. That would be part D. For part E, let's find the mole fraction of helium. This will be equal to the moles of helium, which is the component, over the total moles, which is again 35. Units cancel, and you get 0.571, again to three significant digits. Now, here's a way you could check. Mole fractions, just like percentages add up to 100%, mole fractions also add up to 1. Instead of 100, they add up to 1. If you add 0.429 plus 0.571, it will add up to 1, which you could have also, once you figure out the mole fraction of oxygen, you could have just subtracted 1 minus 0.429, and you would have gotten the mole fraction of the other gas. Okay, now you can only do that if you have two gases, because at the end of the day, they will add up to 1, just like percentages add up to 100. Now here's what we're going to do. So we got our two mole fractions, okay? If you look here, they want now the partial pressure of oxygen and helium. Now if you recall, they gave us the total pressure. The total pressure, 7 atms. There are two formulas that I just introduced to you. To find the partial pressure of oxygen, what you do is you get the total pressure times the mole fraction of oxygen. Okay? So, to find the partial pressure of oxygen, well, the total is 7 atms that was given in the question. And we just found the mole fraction of oxygen, which you saw was 0.429. When you do the math here, you're going to see that you get a partial pressure of oxygen equal to 3 atms when you round it to three significant digits. Okay? That was letter F. Now look at letter G. Let's do the same and find the partial pressure of helium. You do the total pressure times the mole fraction of helium. Let's substitute the numbers. So the partial pressure of helium will be equal to also the total, which is 7 atms again, times the mole fraction of helium, which is 0.571, and you're going to get a partial pressure of helium equal to 4 atms. Now, look how interesting this is. We're going to go full circle with this. Remember that the total pressure is 7, okay? And according to Dalton, if you add the partial pressure of oxygen with the partial pressure of helium, they should add up to the total. Well, think about it. If you add 3 ATMs plus 4 ATMs, you're going to get the total, which was 7 ATMs, which makes perfect sense. And that is what Dalton's law says. The sum of the individual pressures gives you the total pressure. Okay? All right. Let's finish up with a couple of more problems here. And this is just the formulas, the derivatives. Okay? Don't forget to add mole fraction, and don't forget to add partial pressure. Here, I'll do this one here, which we just did with oxygen and the and helium. So that's another formula you might want to add. Okay? All right. Let's do a quick summary. We have 3 sample problems that we're going to finish with. First, we got air is a mixture of nitrogen, oxygen, and trace gases. So we got nitrogen, oxygen, trace, just so you know. Trace gases means that the gases are found in very, very small amounts. We'll call it trace here. And if you look here, as we read the question, they do give us the atmospheric pressure is a fancy way of saying total pressure. So the total pressure is 0.9986. Okay, that's the pressure in the atmosphere, the atmospheric pressure. If you recall, the total is going to be equal to the sum of these other 3 partial pressures. Well, as we continue to read, they do give us that nitrogen is 0.785. Everything here looks like it's an ATM, so let me write ATMs here. Oxygen is 0.177. What we're missing is the trace. So here's what we got to do. We need to add these 2 and subtract from the total. So if we add these 2, we get 0.962 ATMs. Let's subtract that from the total. The total, if you recall, is 0.9986. We're going to subtract that minus the 0.962 that we just got. And when we subtract the difference, which is very small, 0.0366, and of course that's going to be in ATMs, that is going to be the partial pressure of the trace gas. Again, the 3 of these add up to 0.9986. Okay? All right, look at this second example. Here we got a mixture of gases, and they give us some moles here. Okay? So we got neon to start off with. They give us 4.465 moles. Then they give us, the next gas is argon, and they give us 0.741 moles. Then they give us a xenon, and that one is 2.154 moles. And if you recall, if we add these numbers up, we can find the total moles. That's going to be 7.36 moles. Okay, now notice the question wants us to find the partial pressure of all the gases. Now, we're going to end up having to use this formula. That partial pressure, let's say, of gas A is going to be equal to the total pressure, okay, times the mole fraction of gas A. Now, notice they already gave us the total pressure. So that's given to us. What we're going to need to do first is find the partial pressure of each of these gases, okay? So first, let's find neon. Neon is simply going to be the part of neon, which is 4.465, okay, over the total, which is 7.36. And when we do the math, remember, no units here, we get 0.607, okay, as your partial pressure. As your mole fraction. Then we're going to do argon over here. And again, that's going to be 0.741 moles over 7.36 moles. And that will give us 0.101. Remember, no units for these. And then let's do the mole fraction of xenon. and that's going to be 2.154 moles over 7.36, and that's going to give us 0.293, okay? So as we do this, you will see we have the mole fractions of each. Now, if you recall, we also have the total pressure. So here's what we're going to do. Let's go ahead. I'm going to erase this down here for a minute. And if we multiply to find the partial pressure of xenon, what we do is we multiply the total pressure, which is 2 atms, okay, times the partial pressure, which is, the mole fraction, which is 0.607, okay? And when you do that, you get 1.214. If you want, we can leave it as 1.21. If you want to put 1.214, that's fine. 1.21 should be enough. This will be the partial pressure of xenon. That's one of our first answers. Then to find the partial pressure of argon, you will do the same, okay? You're going to go ahead and you're going to get, in this case, it's going to be the total pressure again, okay, times the mole fraction, which is 0.101. Let me put a little parenthesis there. And the partial pressure, let me put here, this is xenon over here. Now we got argon over here. And that one's going to be 0.202. And it's ATMs. Okay, I didn't have room to put the 2 is ATMs. So this is going to be let me write that a little bit clearer. It's going to be 0.202. All right, nope, that didn't come out very good. One more time. This will be 0.202. And then our final one, let's put a little box here, is going to be the partial pressure of xenon. And that's going to also be 2 times 0.293. And when you multiply those two numbers, you're going to get 0.586 ATMs. Now, remember what I told you. Here's a way to check this. If you were to add 1.214 plus 0.202 plus 0.586, you will get a partial pressure, the sum of these partial pressures to equal to this total, which is 2 ATMs. You will get this if you add those 3 partial pressures. Okay? So I want you to keep that in mind. All right? Okay. We have one more problem, and here's what I want you to do. I want you to try this one. All right? I'm going to leave you a hint. We're going to have to use one of the derivatives, and then we'll go over this in the next video. So we got P. What we're going to do is solve for P, and remember that you can put total over here. Okay, we can use this. If you're finding an individual gas, let's say this, you're finding the total pressure. If you're finding an individual gas, let's say gas A, you could use this. That would be moles of gas A. And notice they're being placed, okay, in the same container, so that has the same volume and temperature. Remember about temperature being in Kelvin. I want you to try this problem out, and we'll go over the answer in our next video at the beginning as a review. Okay? So I leave this one for you, and this is a hint as far as being able to use these derivatives to get the answers. All right? I'll see you on the next video.